Okay, so this might be the first video that's going to contain some stuff that you might not have seen in a typical undergraduate linear algebra class. It's going to contain some stuff you have seen, but I think there's going to be a lot of stuff in this video that you probably have not seen if you've only had a typical undergraduate linear algebra class. And there's going to be a lot of theory. I'm going to sort of try to do a mix of either just not giving any proofs of the statements I give at all, or and giving proofs of the statements I give at all, or giving proofs of some of the statements that I give, but also just kind of maybe more along the lines of giving convincing arguments for why these things should be true. In other words, instead of proving it for the general case, I might prove it for a specific case, and then from that, you can kind of see how things are going to look, okay, in the general case. And then the book has the proof for the general cases, but I really want to make sure that you just, the thing that I want from this section is I want you guys to kind of have an idea of the theory and how things work, because that's going to be important for what we do later on when we start analyzing the convergence of these various methods. So if you want more detailed proofs, my colleague John Weeks this semester is teaching Math 640. This is an advanced linear algebra class. If you're taking it, great. If you're not, maybe it's not too late to enroll. But also, if you could take it from him again, that would be great as well. It's a great class, and he's a great professor. So two good things together. I assume it's just going to be double good. All right, so we're going to look at what are called canonical forms of matrices today. That is special ways that we can factor a matrix is one way to look at it. So before I begin, let me say the following. Here's a definition. Two matrices by the way, matrix is the singular, matrices is the plural. So it's not matrices for plural. And one matrix is not a matrix C, it's just matrix. Okay, two matrices, A and B, are similar. That's the term I'm defining, similar, if there is an invertible matrix X, and I actually forgot something here. This part is true, but I want to make sure they have the same dimensions. So two matrices. We're going to say A and B, and we want these to be square matrices, square complex matrices. So two matrices A and B are similar if there's an invertible matrix X, and again, it will be apparent that this also needs to be an n-dimensional matrix, such that A is equal to X times B times X inverse. X times B times X inverse. Okay. So again, two matrices A and B are similar if they share this relationship here. Okay, so we're not saying that A and B are equal to each other, but this similarity is an equivalence relation, and when they are similar, we write something like this: A is equivalent to B. So they're not equal to each other, but similarity is an equivalence relation. Meaning, if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Meaning, if A is equivalent to B, then B is equivalent to A, and if and A is equivalent to itself. That's what it means for something to be an equivalence relation. Okay, so again, two matrices A, B are similar if there is an invertible matrix such that this is true, such that A is equal to X, B, X inverse. Now, there are good things. The reasons we care about similarity transforms, what we're often going to do in practice is we're going to have some situation like this. A is going to be the matrix that we really want to study, and B is going to be a simpler matrix than A. X and X inverse might be as complicated as A are, whatever complicated and simple might mean. We'll see as we go on in this video. You'll see what I mean by simple and complex. Basically, B is going to have some more structure than A has, and we'll give examples of what that means. So in order for this to be useful, there's got to be, like, the properties of A and B are similar. The properties of A need to carry over to B, and the properties of B need to carry over to A. So let's look at some of those. So one of those properties is the following. The eigenvalues and I'm not going to write it, but this does not extend to the eigenvectors. So the eigenvalues of similar matrices are the same. In other words, under this similarity equivalence relation, the eigenvalues are preserved. So the eigenvalues are stable. So if we know that A and B are equivalent to each other, are similar to each other, if A and B are similar to each other, then they have the same eigenvalues. Okay, so let me show why this is true. So let's say I'm going to show that if lambda is an eigenvalue of B, then it's an eigenvalue of A. Okay, so this shows that any eigenvalue of B is an eigenvalue of A. So the spectrum of B is contained in the spectrum of A. Okay, but then notice what we can do. We can write this equivalence relation as the following, as X inverse times A times X is equal to B. And then if I define Y to be X inverse, I can write this as YA Y minus 1 is equal to B. And then the similar argument is going to show that any eigenvalue of A is going to be an eigenvalue of B. Okay, so at first I'm going to show that any eigenvalue of B is an eigenvalue of A. And then by doing this thing here where Y is equal to X inverse, the argument is going to apply just with just with Y's instead of X's, and show that every eigenvalue of A is an eigenvalue of B. In other words, the spectrum of A is included in the spectrum of B. So the spectrum of B is included in the spectrum of A, and the spectrum of A is included in the spectrum of B. Therefore, the spectra for both of the matrices are going to be the same. Okay, so let's do this. So let lambda V be an eigenpair for B. So let lambda and V be an eigenpair for B. Okay, so again, what this means, by definition, what this means is B times V is equal to lambda times V. Okay, and now what we are going to do is we are going to define, I always get this mixed up on the exact order that I need to have things go in. So now, so now we're going to do this following computation. We're going to do A times XV, where that X is equal to this X. Okay, so A times XV. Okay, so we're going to think about doing A times that vector XV. Okay, so now notice what's going to happen. A times XV, well, I can use this similarity relationship. This is XB X inverse. That's what A is. Now I'm going to multiply it by XV. And using the associativity of matrix vector and matrix multiplication, X inverse times X, I can compute that first. That's just the identity matrix. And so this is going to be X times BV. Okay, but what is BV? BV is equal to lambda V. And so this is lambda times XV. Okay, so in other words, if V is an eigenvector for B, then XV is an eigenvector for A, and it has the same eigenvalue lambda. Okay, now lambda is a generic eigenvalue, and so what this shows is that the spectrum of B is a subset of the spectrum of A. And if you skipped the first couple of videos, that's fine. I'll just remind you that the spectrum of a matrix is a set of all of the eigenvalues. So, in other words, what we're saying is if lambda is an eigenvalue of B, it's also an eigenvalue of A. And then via this argument over here, it says if lambda is an eigenvalue of A, it's an eigenvalue of B. And so all of the eigenvalues are the same. But notice the eigenvectors are different. So this tells how the eigenvalues transform. Okay. So if we have an eigenvector of B, x times V is going to be the corresponding eigenvector for A. Okay. So this is that is an important fact there. Okay, again, the fact that the eigenvalues are stable under this similarity relationship is going to be sort of something that we use throughout this class. Okay. So the kind of best similarity relationship, I'm going to try to leave this here just so we can have this as a reference. So the kind of easiest similarity relationship, the best okay, and I'm gonna both underline best because it really is good when this can happen, and put air quotes around best because everybody gets to decide what's best. So or something, I don't know. The best similarity relationship is when B is diagonal. Okay, so what does that mean? Let me just write it. So we're going to have A is equal to X times D times X inverse. So I'm using the letter D instead of B because it's diagonal, and diagonal starts with D. What is a diagonal matrix? Well, hopefully you remember this. It's going to be a matrix where you have possibly non-zero entries on the diagonal, and everything else is going to be equal to 0. Okay, so it's not quite the identity matrix or even a multiple of the identity matrix, but it's like the identity matrix in the sense that aside from the diagonal, everything is equal to 0. And then on the diagonal are going to be the only non-zero entries. Okay, so this is sort of the equivalence relation that we like the most. Okay, let me just explain one of the reasons that we like when this equivalence relation is true. Okay, because we're going to be doing the following a lot. And we're going to look at a more complicated version when we cannot write a matrix this way. So this is a very good case when we can say A is equal to XD X inverse. In this case, we say that A is diagonalizable. Let me give you one reason that we like this. Okay, practically speaking, we are going to want to compute things like A to the power of K for this class. Okay, if I can write A this way, notice this is just going to be equal to X D X inverse to the power of K. Okay, but notice what happens if I actually sort of write these factors out. I'm going to have XD X inverse X D X inverse all the way down X D X inverse. I have this K times. Okay, so there's K different factors here. But again, notice that because of the associativity of matrix multiplication, I can just get rid of these parentheses and just write the product like this, and then do the computations in whatever order I want. So for example, I can X inverse times X, they cancel. It's just the identity matrix. That X inverse is going to cancel with another X inverse that's in the dots. This X is going to cancel with an X inverse that's in the dots. And so what we're left with is X times K different copies of D times X inverse. And this is just X times D to the K times X inverse. Okay, now here's something. If you look at this matrix and raise it to the power of K, you can do this as an exercise. You know, usually when we take a matrix and we square it or raise it to the power of k, there's not an easily discernible relationship in the entries of a to the power of k to the entries of a. But for diagonal matrices, this is not true. The thing that is true for diagonal matrices is exactly what you want it to be. D to the power of k, well, all we do is we raise the diagonal entries to the power of k. Okay, so now a to the power of k in general, there's no way, you know, if we just try to compute a to the power of k by doing repeated matrix multiplication, we just have to do this k times. Okay, but in a case where the matrix is diagonalizable, we can do this much easier thing. Just compute the diagonalization, which might take some time, but you just do it once, and then a to the power of k is going to be given very simply by this formula here, where all we're doing is just raising the entries to the power of k. Okay, anyways, so this is one use. This is one way, one of the reasons that we like diagonal matrices, and a lot of the this is the reason that we like matrices that are diagonalizable, and it turns out that a lot of the matrices that we're going to be talking about in this class are diagonalizable. Okay, so when is a matrix diagonalizable? So this is a great thing that we can do. So when can we do this? Or really, it should say, for which matrices can we do this? For which A can we do this? In other words, what are the properties that A has to have in order for there to be a diagonal matrix that A is equivalent to? Okay, well, this is actually a somewhat difficult question to answer. There's a lot of sufficient conditions. If a matrix satisfies this property, then it is diagonalizable. Okay, we're going to give, but maybe not a lot of necessary conditions. So as we will see, if a matrix is Hermitian, then it is diagonalizable. If a matrix is normal, then it is diagonalizable. Those conditions, like you can look at a matrix and just look at the entries of a matrix and tell whether or not it is Hermitian. You don't have to do any computations really. You just look at a matrix. If it is Hermitian, then you know that it is. Sorry, not Hermitian. Symmetric. If a matrix, if a matrix is if a matrix is equal to its adjoint, AH. So, in that case, you know, I will write that down in just a moment, actually in a later video. But there are some theorems that you can determine whether or not a matrix is diagonalizable just by looking at it. That will give a sufficient condition. If the structure of the matrix satisfies this certain property, then it is diagonalizable. In other words, there's a diagonal D that it is similar to. Okay, but there's not a grand theorem that says if a matrix satisfies this very easy to verify property, then it is diagonalizable. About the best thing that we have that gives an if and only if, that is a necessary and sufficient condition, rather than just being necessary or just being sufficient, is the following. So theorem, a matrix, Hermitian is the right word. So I always, for some reason, I always confuse the words Hermitian and unitary in my mind. Little embarrassing, but a matrix, if a matrix is Hermitian, then it is diagonalizable. Okay, anyways, but that's not an if and only if condition. There are matrices that are diagonalizable that are not Hermitian. A matrix is diagonalizable. A matrix is diagonalizable, which means, i.e., there is a diagonal D such that A is similar to D, where the similarity relationship is what I have erased here. A matrix is diagonalizable if and only if, which I'm just going to abbreviate IFF, A has in linearly independent, and again, I'm going to abbreviate this EVEX eigenvectors. Okay. So a matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so you might be thinking, well, I thought you just said there was no theorem really that says like an if and only if condition, and this is an if and only if condition. Well, what I mean is in order to determine whether or not a matrix is diagonalizable, you have to compute all of its eigenvalues and eigenvectors. That's quite a bit of computation involved. When I say there's no like grand theorem about just whether or not a matrix is diagonalizable, I mean something like where you can look at the matrix, you can just look at the matrix and tell right away whether or not it's unitary, or whether or not it's Hermitian, or whether or not it is symmetric. There's another condition: if a matrix is normal, it's diagonalizable. Remember, that just means that A commutes with its Hermitian adjoint. Okay. And again, that's just doing one computation to show, or two computations to show that AHA is equal to AAH. Okay, but this right here requires the computation of a bunch of eigenvalues and eigenvectors, which is, it's harder than just looking to see if a matrix is Hermitian. All right, so now I want to prove this. But this is nevertheless an important fact. Okay. So let's first assume, that it has n linearly independent eigenvectors. So assume A has the eigenpairs lambda 1, v1, comma, comma, lambda k vn, and we're going to assume that they are linearly independent, and we're going to assume that this set of vectors v1 through vk are linearly independent. Okay, so we're going to assume the vectors v1 through vk are linearly independent, and we're going to define. We're going to make these following definitions. The matrix X is going to be the matrix whose columns are the eigenvectors, and the matrix D is going to be the matrix of eigenvalues. Okay, so lambda 1 goes along with the eigenvector v1, lambda 2 goes along with the eigenvector v2, and so on and so forth. All right, so I'm going to have to continue up here. Okay, so my claim, let me write my claim down here. My claim is that hold on one second. Yes, my claim is that A is equal to X D X inverse. So my claim is that A is equal to X D X inverse. X D X inverse. Okay, so why is this true? So let's begin with the following observation. If I let EK be the standard basis vector, so it's going to be zeros, it's going to be all zeros except for a 1 in the kth position. Okay, so that's just going to be a notation that we use throughout the semester. EK is sort of, we call it a standard basis vector. It's the vector of all zeros, except in the kth position there's a 1. So notice that if we do X times EK, well, this is going to be 0 times the first column of X, plus 0 times the second column of X, plus dot, 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 plus 1 times the kth column of X, plus 0 times the k plus 1 column of X, and so on and so forth. So X times EK is just equal to the kth column of X. But what is the kth column of X? It's just equal to VK. So this is equal to VK. So X times EK is equal to VK, or EK is equal to X inverse times VK. Okay. All right. So now notice what happens if I do A times VK. Okay, if I do A times VK, I can if I do A. So then my claim is that if I do A times VK, this is equal to lambda K times VK. And this is for K equals 1, 2, up to N. This is my claim. I haven't proven this, but this is my claim. Okay, so AVK is equal to lambda K VK. Now, on the other hand, if I do X D X inverse times VK, well, what am I going to get? Well, X inverse times VK is just equal to EK. So this is equal to X D times EK. Okay, well, let's think about what's going to happen here. D is a diagonal matrix. D times EK, again, is going to be 0 times the first column of D, plus 0 times the second column of D, plus dot, 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 plus 1 times the kth column of D, plus 0 times the k plus 1 column of D, and so on and so forth. So this, what is the kth column of D? This product here, D times EK, is just going to be the kth column of D. What is the kth column of D? Well, if we come over here, it's going to be the column where there's zeros everywhere except for lambda K in the kth position, and then 0 everywhere else. So this is going to be lambda. This product here, D times EK, is equal to lambda K times EK. And then we can move the lambda K over there. We're going to get lambda K times X to the EK. But what is X to the EK? X to the EK is equal to VK. So this is equal to lambda K VK. All right, so what we've just shown is that A times VK is equal to XD X inverse VK. So I'm going to write that here. So this is equal to XD X inverse VK like this. Okay. And this is for all of the vectors V1 through Vn. Now, V1 through Vn, there are n of them, and they are linearly independent, so they form a basis for Cn. So, what this tells us is A times Vk is equal to XD X inverse times Vk for all vectors in a basis for Cn. So then, A times V is equal to X D X inverse times V, and this is for all vectors in Cn. Okay, so why is that? So I'm saying if A times Vk is equal to XD X inverse times Vk for all vectors in a basis, then that's going to be true for all vectors in Cn, and it's simply because we can decompose V in terms of the Vk. Okay, so now what this means is these two matrices are equal to each other. What does it mean for two matrices to be equal to each other? Well, if you do A times that and that times that, if this equality is true for all vectors in Cn, then the matrices are equal to each other. That's what one of the things it means for a matrix to be equal, for two matrices to be equal to each other. Okay, another way to see this is that the Kj entry of A is the inner product, the standard inner product of EK with EJ. This will give you the Kj entry, and since A times e to the k, if I use V here for e to the k, then I can write this as X d X inverse e to the k e to the j, and these two things have to be equal to each other because of this relationship here, and so it says the Kj entry of A is equal to the Kj entry of XD X inverse. In other words, the matrices have the same numbers in them, so they are equal to each other. Okay. So this shows that if A has linearly independent eigenpairs, linearly independent eigenvectors in linearly independent eigenvectors, then it's diagonalizable. Okay, on the other hand, let's show the other way. Okay, let's assume if A is equal to x d x inverse, then we want to show that A has in linearly independent eigenvectors. Okay, so note the eigenpairs, I'm just going to abbreviate this as E pairs. The eigenpairs for D are the following. The eigenpairs for D are the following. Lambda 1, E1, lambda 2, E2, all the way up to lambda n, En. Okay. Okay, now my claim x ek is an eigenvector for A. Okay. Sorry, I want to find a new marker. This one is not doing its marker things. Okay, so why is that? Well, now I'm assuming that this relationship is true. So we look at A times x ek. Okay, what, A times x ek using the diagonalization. This is x d x inverse times x ek. Again, associativity says those are equal to the identity matrix. So this is x times d times ek. Well, again, if you believe this over here, and you should verify this for yourself, that these are the eigenpairs. Ek is an eigenvector of D, so this is going to be x lambda k ek, which is equal to lambda k times x to the ek, which again, this is equal, so in other words, A times x ek is equal to lambda k times x ek. So in other words, it shows that x ek is indeed an eigenvector for A. Okay, now the other thing, I'm not going to prove this. This is something that you should prove on your own, please. That the set x e1 up to x en is a linearly independent set. So anytime you have a set of vectors, let's say e1 through en, let's say here e1 through en means the standard basis vectors, but if they just meant any linearly independent set, if you have any linearly independent set of vectors and multiply them by an invertible matrix, then that new set of vectors is also going to be linearly independent. And that's a fact that you should prove for yourself. Think about why that's true and prove it for yourself. Okay, so these are then going to be linearly independent. Okay, so each one of these, x e to the k, is an eigenvector for A, and it's a linearly independent set, so therefore A has in linearly independent eigenvectors. Okay, so what's the sort of backup for when a matrix is not diagonalizable? We will see later this week other conditions that make a matrix diagonalizable, that will imply a matrix is diagonalizable. Like I mentioned before, the two main ones are going to be that a matrix is normal, or that a matrix is symmetric or Hermitian. Will give us that a matrix is diagonalizable. But we really want to know what happens. What happens in the case when a matrix is not diagonalizable. One of the places where this might have come up in your math education, if you've taken a differential equations class, If you remember looking at systems of equations in a differential equations class, remember that things are great if there are distinct eigenvalues or complex eigenvalues, but in the 2 by 2 case. But if you have a repeated eigenvalue and there's only one eigenvector, you have to do this thing with a generalized eigenvector. In that case, the matrix of the differential equation was not diagonalizable. Okay, so now we're going to look at the Jordan form of a matrix. So first, let me get a definition out of the way. A Jordan matrix is a matrix of the form J equals J1 down to, I'm going to say, Jm with zeros here and zeros here. Okay, in each one of these matrices, each one of these entries, it looks like it's on the diagonal. Those are actually matrices, where each JK is something called a Jordan block. It's going to be a square matrix, and we're going to have all lambdas on the diagonal. So the same lambda on the diagonal. It's going to have ones on the diagonal above the diagonal, so it's called like maybe the super diagonal, and zeros everywhere else. Okay, so for example, a 2 by 2 Jordan block, these are called Jordan blocks, would look like this: 0, lambda, lambda 1. That would be a 2 by 2 Jordan block. A 3 by 3 Jordan block would be lambda 1, 0, 0, lambda 1, 0, 0, lambda. Okay, and then maybe let me make this into a 4 by 4 Jordan block. You'd have something like this: a 0 here, a 0 here, a 1 here, and then 0, 0, 0, lambda. This is a 4 by 4 Jordan block. Okay, so on the diagonal we have lambda, the diagonal we have lambda, and then the diagonal above the diagonal we have ones and then zeros everywhere else. Okay, so then what is this sort of matrix going to look like then? Well, this matrix is going to look like the following. So we're going to have lambda, let's see, maybe lambda 1 down to lambda 1, and then we're going to have lambda 2 down to lambda 2, and then, down to lambda, what do I have here? M, and then we're going to have ones on the diagonal, on the super diagonal, and then zeros everywhere else. Okay, so let me just give you an example of what a Jordan matrix might look like. So maybe we're going to have a 2 by 2 Jordan block, so we can have a lambda 1, a 1, a 0, a lambda 1 here, and then maybe we'll have, let's say I'm going to make a Jordan matrix where we have a 2 by 2 Jordan block and a 3 by 3 Jordan block. So we're going to have this. And then for the 3 by 3 Jordan block, let's say it's lambda 2, level 1, and a 0, 0, 0, 0, lambda 2, and then a 1, and then 0, 0, 0, 0, lambda 2. Okay, so we have a 2 by 2 Jordan block and a 3 by 3 Jordan block. So this is like a 2 by 2 Jordan block, and this is like a 3 by 3, or not like a 3 by 3, that is a 3 by 3 Jordan block. And those lambdas could be equal to each other, like the lambda 1 could be equal to lambda 2, or they could be distinct. It depends on properties of the matrix. Okay, and so notice that for each Jordan block, the super diagonal are going to be 1. So here, the super diagonal here is 1, the super diagonal here is 1. But it does not mean that the super diagonal for the entire Jordan matrix is going to be 1. So notice that that's 0. That is on the super diagonal, but it is not equal to 1. Okay, so the Jordan blocks all are going to have all ones on the super diagonal, but the Jordan matrix itself is not going to have ones on the super diagonal. Okay, so here's a fact. if A is an n by n matrix, then A is equivalent to some Jordan form. So any matrix is equivalent, is similar, a similarity is an equivalence relation, so sometimes we say equivalent. If A is an n by n matrix, then it is similar to some Jordan block, and the diagonals, the diagonal entries of J are the eigenvalues of A. Okay, so J here, remember we talked about we like similarity transforms or similarity relationships because we want that middle matrix, that B in the notation that I had before, to have an easier structure than A. And that's exactly what we have here. The Jordan normal form, this is called the Jordan normal form of the matrix, or the Jordan canonical form of the matrix. It's really only called the Jordan canonical form if these eigenvalues are ordered in increasing order, but we'll forget about that for now. Every matrix has a Jordan canonical form, eigenvalues on the diagonal, and again, this Jordan canonical form is not diagonal, but it's like almost diagonal. It's very close to being diagonal. We just have these ones on the super diagonal. Again, we really want this matrix to be diagonal, but not all matrices are diagonalizable, but every matrix is similar to its Jordan canonical form, or a Jordan canonical form. This is just one example of it. Okay, one example of a Jordan canonical form. Okay, so one of the reasons that we like a Jordan form, so let's think in terms, I did that example before where I computed the a to the power of k using the using the diagonalization. Well, let's just see how this will go for the Jordan canonical form. So again, a to the power of k is equal to x times j to the power of k times x inverse. Okay, so how is this going to go? Well, what we do, if we have a matrix J, which is equal to J1, has it made up of all of these blocks like this, to the power J1 through Jm. If I raise this to the power of k, all this is doing is raising each of the blocks to the power of k. Okay, so it's very similar to how the diagonal works. Okay, so convince yourself that this is true. If you have a Jordan canonical form, again, there's all zeros here. Okay, if you have a Jordan matrix, and you raise it to the power of k, all that is doing is raising the Jordan blocks to the power of k. This is probably something that you learned, this is probably something that you did not exactly learn in your linear algebra class. You might have learned it, you might not have learned it, I don't know, but this is it here. This is something that when we need to talk about it more, I will give a little more detail on it than I am now, but I just want to sort of soften the ground, so to speak. A lot of the matrices we're going to talk about are going to be, actually be diagonalizable. Okay, so this is what we have here. So now if we want to study powers of a Jordan matrix, we can see just what's going to happen for powers of Jordan blocks. Okay, so let's see what's going to happen here. So let's say I have a 2x2 Jordan block, lambda, 0, lambda, and I want to square it. I'm going to have lambda, 1, 0, lambda. And if you do this, you see you're going to get lambda squared here, 0, lambda squared here, and 2 lambda here. Okay, now let's say you want to cube it. So we're going to multiply this. So we're going to have lambda squared, we're going to have lambda squared, 2 lambda, 0, lambda squared, times lambda, 1, 0, lambda. And when you do this, you're going to get lambda cubed, 3 lambda squared, 0 lambda cubed, like this. Okay, and in general, the 2 by 2 Jordan block has the easiest form. If we do this to the power of k, this we're going to have lambda to the power of k here. We're going to have k lambda to the k minus 1, 0, and lambda to the k here. Okay, so I'm going to leave this here. I want you to prove this. Take a minute to prove this by induction. Prove that this is true, and proving it by induction is going to be the easiest way to do it. Okay, so what this tells us then is when we raise this Jordan to the power of k, if these are all 2 by 2 matrices, then we know that the diagonal of this matrix is all going to be the diagonal to the power of k. And the thing above the diagonal is just going to be this k times lambda to the power of k minus 1, or it's going to be equal to 0. Because the diagonal of the Jordan matrix is either, everything on this super diagonal of the Jordan matrix is either a 1 or a 0. Okay, and that's what we're going to have here. And I'm not going to show you what the formula for a 3 by 3, 4 by 4 matrix, and so on and so forth, a 3 by 3 Jordan block, a 4 by 4 Jordan block, and so on and so forth. Gets a little more complicated, but it is going to be something very similar to this. Okay? All right. So the Jordan form, I'm going to use the Jordan form because I want to use it to prove something that is going to be somewhat relevant to some of the things that we're going to talk about in this class. And it's the following theorem. The matrix A to the K converges to the 0 matrix if and only if the spectral radius of A is strictly less than 1. So that matrix converges to 0 if and only if the spectral radius of A is less than 1. Okay, so when you say a matrix converges to the 0 matrix, we mean that all of the entries of the matrix converge to 0. Okay, we say a matrix converges to the 0 matrix if and only if every entry of the matrix converges to 0. Okay, so let's think about why this is true. I'm going to prove the harder direction first. That is, I'm going to assume that rho of A is less than 1, and I'm going to prove that the matrix converges to 0. Okay, and really when I say I'm going to prove this, I mean something more like I'm going to give a convincing argument for why this is true. Okay, so A to the power of k, using what I have over here, is equal to x times j to the power of k times x inverse. So, if I want to show this goes to 0, it's enough to show that jk goes to 0. So it is enough to show that jk converges to the 0 matrix. Okay, because if this converges to the 0 matrix, then x times 0 is equal to the 0 matrix. Okay, so it's enough to show that jk converges to the 0 matrix. But given that j to the power of k is just equal to j1 to the power of k all the way down here to jm to the power of k and 0 everywhere else, it's enough to show that a Jordan block if J is now a Jordan block, let's say Ji, take one of these Jordan blocks, goes to 0. Really that all Jordan blocks converge to 0. So not just a Jordan matrix, but like the Jordan block. Okay. Well, why does this converge to 0? Okay, so I'm going to come over here and now give a convincing argument. Now, all of the Jordan blocks are going to be like this or bigger, 2 by 2, 3 by 3, 4 by 4. If we just look at a Jordan block, why does this converge to 0? Well, remember, lambda is an eigenvalue. If the spectral radius of A is less than 1, it means the absolute value of these eigenvalues are going to be 0. Sorry, the absolute value of these eigenvalues is going to be less than 1. The complex modulus of these eigenvalues, let me say, is going to be less than 1. Okay, so clearly, if the absolute value or the complex modulus of lambda is less than 1, and you raise it to the power of k, it's going to go to the 0, right? 1/2 to the power of k goes to 0 as k increases. 1/2 I, 1/2 plus 1/2 I, that is going to converge, 1/4 plus 1/4 I is going to converge, to the power of k is going to converge to 0. Okay, so this is clearly going to converge to 0. That's clearly going to converge to 0. Now right here, what's happening as k gets bigger, this k is getting bigger, but this is also getting smaller. Okay, and so you can use L'Hopital's rule or something like that to prove this also converges to 0 as well. Okay, and then like I said, similar things are true if you're looking at a 3 by 3 or a 4 by 4 or more general canonical, a general canonical block. It's also you're also going to have formulas like this, and you can also show that each entry is going to converge to 0 as well. Okay, the book gives a very nice argument for why this is true in general, but this is what's happening. I'm showing you what's happening with the 2 by 2 matrix, and hopefully you can see why for a 3 by 3 or a 4 by 4 or a 5 by 5 Jordan block, similar things are going to happen. And that's assuming that you believe me there, or at least can see how things are going to work. I don't want you to just believe me. I want you to sort of see how things are going to work. It shows that for any Jordan block, this is going to go to 0 as k goes to infinity. Okay, and so therefore a goes to 0. Okay, so now I'll just briefly show the other way. Well, no, I want you to prove the other way. But the thing that I want to show you is, so we want to show, assume, oops, this marker is now not working great for me. So assume that a to the k goes to 0. Then we know that a to the k times any particular vector is going to go to the 0 vector. Okay, because if a is going to the 0 matrix, a times any fixed vector is going to be going to the 0 matrix. Sorry, is going to be going to the 0 vector. Okay, use that to show that the spectral radius must be less than 1. Okay. Now, this is important because this class is called iterative methods, and so we're going to be doing iterative. You might suspect we're going to be doing iterative matrix multiplication. That's at least one of the things that we're going to be doing here. Okay, and so knowing something like this, that this converges to 0 if and only if the spectral radius is less than 1, is something that will be helpful. Knowing things like this is something that's going to be helpful for us. Okay, let me just look through my notes here to see the next thing that I want to say. Yes, okay. This, I believe, is the last thing that I want to say in this video. So, theorem. Okay, so theorem, the sum of this series, k equals 0 to infinity, a to the k converges if and only if the spectral radius of a is less than 1. And in this case, it converges to the inverse of I minus a. Okay, so think about this in terms of series. If you just go back to like Calc 2, if a is equal to x, we have the sum of x to the power of k. Think about what that's equal to. Stop this video and think about what that's equal to, and show why this is exactly the thing that you should expect. Okay, so I just want to talk about this a little bit. I'm only going to prove that it converges to this. Now, why does it converge? Well, if it converges, we know that these terms have to go to zero. That's just sort of what that's one of the, remember the test for divergence for series. If a series converges, then the terms go to zero. Okay, so if this converges, the terms have to go to zero. That is, each of the matrices has to go to zero in this. And well, if the matrices go to zero, then rho of A is less than zero. Now the other one is not the other direction. If we know that these converge to zero, if we know that rho of A is less than 1, we know that A to the k converges to 0. That itself is not enough to show that this sum converges. But if you go back to the Jordan canonical form and look at the Jordan canonical form, you will show that each individual entry converges as well. Okay, because what are you going to get, like for a 2 by 2, if you look at it as sum k equals 0 to infinity, if you look at something like lambda 1, 0, lambda, if you just look at one Jordan block, what is this going to be? Well, when I do this computation, when I raise this to the power of k, I'm going to get lambda to the power of k, k lambda to the power of k, 0 lambda to the power of k. And when I sum these up, when I sum this up, I'm just summing up each individual term, and I know that each of these terms is going to converge. Lambda to the power of k, that sum converges, and k times lambda to the power of k converges as well, and you can compute even what it converges to. Anyways, so again, that's sort of should be not construed as a proof, just sort of a convincing argument if you think through what I'm saying, that if we know the spectral radius is less than 1, then this is going to converge. Okay, but why does it converge to this, to the inverse of I minus A? Well, all we're going to do is just do I minus A times this sum, k equals 0 to infinity, A to the power of k, and we're just going to show that this is equal to the identity. If this is equal to identity, then by definition, this is equal to the inverse of I minus A. Okay, so by the distributive property of matrix-matrix multiplication, this is just going to be the sum k equals 0 to infinity, A to the power of k, minus A times the sum k equals 0 to infinity, A to the power of k. Okay, and now A is a constant as far as k is concerned. So I can move this, I can distribute this A inside the sum. So we're going to have something like this. But now notice what's going to happen. I can write this in the following way. This is the sum k equals 0 to infinity, A to the power of k. This sum is starting at k is when k is equal to 0, that's to the power of 1. Okay, so I can reindex things and write this as k equals 1 to infinity. Essentially what we, or not essentially, but what we have here is a telescoping series. And now notice this term, this sum has a k equals 0 term, but this sum doesn't, but otherwise they're all equal. So all we're going to be left with is the k equals 0 term here, which is A to the power of 0, which as you might expect just means the identity matrix. Just like x to the power of 0 is 1, A to the power of 0 is equal to the identity matrix, if it's not the 0 matrix already. Okay, so I minus A times this series is equal to the identity matrix. That shows that this is equal to I minus A to the power of minus 1. Okay, again, this is going to be something that we will use in this class, which is one of the reasons that I'm telling you about it here. Okay, so like I said, this video was one of the first videos where I talked about things that are not typically covered in a standard, or that might not be typically covered in a standard undergraduate linear algebra class. So I went a little bit slower, but in the videos after this, I'm going to slow down maybe even a little bit more for the linear algebra review, because it might be getting into a position where for many of you, it's no longer review, but you're more or less seeing something new. But again, what I really want to do is I want to give you the tools of linear algebra that we will use for the stuff that we're going to be doing in this class. And so my main goal then is to just show you facts, show you concepts, make movements and give some sort of convincing arguments for why the things I'm saying are true. If you want to know more about it, just sort of read about that on your own. But my main thing is just to give you the tools, and not necessarily prove 100% why the tools work. There's other classes that we have for that. I want to give you a toolkit for things that we're going to be doing later on.